Jacob Andreas is an associate professor at MIT in the Department of Electrical Engineering and Computer Science, as well as the Computer Science and Artificial Intelligence Laboratory. His research aims to understand the computational foundations of language learning. Language is definitely a passion for Jacob, and build intelligent systems that can learn from human guidance. And I see you've passed the general intelligence test of plugging in your slides, so I will turn it over to you.
Cool, thanks a lot. So this is not going to be really a talk about play or games, but is about evaluation and sort of broader questions relating to evaluation. Suppose you go to the best LM or approximately the best language model you can get your hands on today, and you ask it the following question. Was S. Chalapundian first appointed Speaker of the Madras Legislative Assembly in 1962? Give us both an answer and a numerical estimate of your confidence. If you ask this question to GPT-5, it says yes, and it says it's 64% confident in that answer. Now, this output, I think, is remarkable for a couple of reasons. The first is that it's actually the correct answer to this question. The model does this without using web search, and we have today systems that know sort of so much about facts in the world that they can answer trivia questions about everything from math to biology to like mid-century South Indian politics. The second thing here is that the model is not just answering this question, it's performing a slightly more complicated task. We've asked it for an output in a particular format, both an answer and a numerical confidence. This is not what most of the sort of question answering data in the training data probably looked like, and yet we've gotten a sensible looking answer. However, if we start to probe this model's knowledge of related questions, the picture gets a little bit more complicated. For example, if we just change the year here and ask this model the same question, it believes the answer to this new question is also yes, and it is even more confident in this new answer than in the previous one. So I want to claim that two different things have gone wrong here. The first is a factual inconsistency, right? Obviously, if the answer to the first question was yes, the answer to the second question has to be no. And, the main takeaway here is that even when we apply the sort of training procedures that we have today to what is, to a first approximation, the entire corpus of knowledge written down by humans over the course of human history, they still make these kinds of mistakes. And we would like to catch these kinds of mistakes, and we, ultimately would like to fix this sort of problem. The second error is more subtle, and it's what we might call instead an error of metacognition, right? Whether or not the model is correct about the first question. If it thinks the answer to that question is more likely than not to be yes, then it shouldn't also assign very high confidence to other, sort of other contradictory statements when we ask it those statements in other contexts. So to put this another way, right, these errors of factual consistency reflect in some sense the fact that this language model has a poor model of the world and what's true in the world and what is possibly true in the world. And these inconsistent confidence scores reflect in some sense the fact that the model has a poor model of itself and the things that it knows or doesn't know and sort of what the evidence is for those things. Now, the question of how and whether language models or any other AI systems that we have today represent the world and how they represent themselves have gotten a lot of attention in the last couple of years. Right now, there's a huge amount of disagreement within the community about what it even means for, a language model or a neural network or an AI system more generally to possess a world model, or what features we should expect world models to possess. But if we think about analogies to the kinds of models that humans build of the world around us, the kind of models that we use for sort of interacting with the environment, accuracy is often not the most important consideration here, right? Models, almost by definition, are abstractions of what's true in the underlying world. They discard information about the system being modeled. They don't let us answer every possible question we might want to answer about that system, right? They're useful for only answering a limited set of questions. But what they do possess is coherence. If I ask the same question in two different ways, or if I ask two questions whose answers depend on each other, what makes a model a good model is that it's going to give me, sort of consistent answers to both of those questions. And I think really throughout the history of science, building the task of trying to build internally coherent models of the world, even if those models can't explain everything or don't actually line up exactly with the data that we have available to us, is actually how we get accurate theories, and in turn how we make accurate predictions about how the world works. So what if, instead of just optimizing models for accuracy the way we do today, we tried to explicitly train them to be coherent in this sense? This is mostly not a modeling talk, and I want to get through this bit quickly, but show a couple of vignettes about what it might look like to optimize for coherence in this sense. So with respect to the question of modeling a world, we can, maybe come up with a really simple procedure for optimizing for factual consistency. What I'm showing here is work led by Faiza Akurek with some collaborators at BU. And what we're going to do here is the following. We're going to pick some topic, say, sort of the Japanese history. We're going to prompt a language model to write down all of the facts that it knows about that topic, whether or not these facts are internally consistent or not. We'll use the same model to reason about those facts, identify the subset of them that is both internally coherent and most likely on the margin to be true. And importantly, the second step is a really easy task, right? Something we've been able to do with models for a very long time is this basically syntactic task of looking at a pair of sentences and figuring out whether one of them entails the other or whether they contradict each other or whatever. And that's essentially all we're having to do in the second step here. But by doing so, we can identify a sort of subset of statements here that are both maximally likely to be true and internally consistent with each other. And having done so, we can just retrain the same model on its essentially own output or its own judgments here to assign higher probability to higher probability to those statements that were judged on reflection to be most likely to be true, and lower probability to those things that were judged to be false. Now, pretty remarkably, when we evaluate these kinds of models trained in this way, totally self-supervisedly on fact-checking tasks, we actually get improvements in accuracy just by optimizing for internal consistency. But I think more importantly here, if we look at what happens, and the bottom half of this table is just 3 different flavors of the same procedure that we looked at. If we look at pairs of very similar and closely related statements that are mutually contradictory, and we count the number of these that the model, assigns a truth value, or says are both true or both false, that quantity also goes dramatically down as a result of this kind of optimization procedure. So something that we can do to optimize for consistency. That's about models of the world. What about these sorts of models of the self? And if we think about what went wrong in the example that we started this talk with, it was that the model's confidence in its own outputs, whether right or wrong, was too high. And this turns out to actually be a sort of expected outcome of the kinds of reinforcement learning procedures that we use for training reasoning models, especially today. So what can we do instead? This is work led by Mehul Damani and Isha Puri in collaboration with some folks from Yoon's Kim's group here, as well as IBM. Basically, just change the reward function so that models don't only get points for getting right, but also getting points for being correct and assigning high confidence to their answers, and give them partial credit for being wrong, but assigning low confidence to their own answers when they're wrong. And when we train models in this way, again, without any data beyond what we would sort of normally need for reasoning training, you get models that are both more accurate, but also better at assessing how likely their own answers are to be correct. But only up to a point. So what we're looking at on this plot, this is I think my favorite one from this project, is if we take a question and we sample a bunch of different answers to that question, and for each of those answers we ask it the probability that that's the correct answer, and then we sum all of those probabilities up. And what you can see is that even after this fancy reasoning procedure, which are the pink dots here, you can find on some of these data sets of answers, each of which the model assigns, say 100% probability to, such that the total probability of all of the answers the model is willing to say is true is like 1,500%. And so clearly we're still not getting models into a state where they actually really know what the full space of answers is and what kinds of things they think are likely or not. So what does all of this have to do with ARC? And here we're looking at the earlier version of the benchmark on these kinds of static tasks, but I think this is true also of the newer version of the task, the sort of interactive one, that at the end of the day, what we are asking models to do here and what we're evaluating models on is their ability to fill in this grid on the right with sort of colors in the right shape, or in these interactive environments to take the right set of actions in the world that correspond to winning the game. That there is something that the model needs to do or something the model needs to predict, and that's the ultimate measure of whether it succeeded. And I think this is true of a lot of the kinds of abstract reasoning benchmarks and reasoning benchmarks more generally that people have developed for AI in the modern era. If we look at sort of the grandfather of all such benchmarks, which are the Bungard problems from way back in the day, have people seen the Bungard problems before? Quick show of hands? No? Okay, so I guess anyone who has read Douglas Hofstadter, which maybe nobody does anymore, has probably encountered these before. Very similar flavor, right? We have a set of objects on the left, we have a set of objects on the right. There's some pattern that separates the things on the left from the things on the right, and while the slide is up, I encourage you to figure out what the pattern is here. And the goal in these tasks, right, is to figure out what that rule is. Importantly here, there is no test set, there is no prediction that you have to make in order to do well at one of these tasks. It is entirely about explanation, about coming up with some sort of rule that would in principle allow you to separate future versions of, or future objects on the left from future objects on the right. But really what we care about are not predictions. What we care about are explanations. What we care about is having some underlying model of what the sort of rule that separates the things on the left from the things on the right are. And I think what we really want to evaluate in a lot of these kinds of reasoning tasks in general is not just, do you know how to sort of fill in this box in the right way? But do you know more generally when you've solved a problem? Do you know how you've solved a problem? Do you know why the answer that you've come up with is the right one? And so I guess what I want to say here is that I think that these benchmarks, and like especially these new sort of interactive game benchmarks, are really fruitful test beds for a lot more than just saying, can you beat this game, but really getting at these deeper sorts of why questions, right? What we really want at the end of the day are models that can solve entire classes of problems, but also explain maybe both their solutions and at an even more sort of meta level, what kinds of algorithms they use for arriving at those solutions. You know, thinking back even to the sort of optimizing for factual consistency that we looked at before, what we're really doing there is optimizing for a model that can articulate not just a set of true facts, but maybe a set of premises and deduction rules that cause you to believe that a given fact is true. And I think this is related to many of the themes in Sam's talk, but we can think about doing this in the context of gameplay also, right? Solving a game means not just taking the right actions, but being able to articulate general principles from which the right actions can be derived and which will cause you to take the right actions in related situations. And so I think there's a bunch more that we can do with evaluation here beyond accuracy, really looking at these sort of model level properties rather than answer level properties or prediction level properties, measuring whether models can give consistent answers across contexts, when there are procedures involved, making sure that they can both implement and describe those procedures. When there are predictions involved, making sure that they can articulate the decision rules that underlie those predictions. And ultimately, I think, when we think about what AI is for, what we want AI to be for, it is about humans and helping humans do things. And a really important principle here is also building systems that are human compatible. An important part of human compatibility is predictability. We might prefer, for example, a system that performs worse, but it's easier for us to interact with. And this, I think, is also the sort of thing that we want to be optimizing for in modeling. And one of the reasons I'm really excited about these new benchmarks that are coming out is that we're going to be able to use them to answer these kinds of questions as well. And I'll wrap up there. Thank you.